Hello, today I'll be presenting on biased user history synthesis for personalized long tail item recommendation. This work aims to improve recommendation systems by addressing the long tail problem where less popular items or tail items are often overlooked. Recommendation systems are essential for online platforms such as streaming, social media, and e-commerce. They connect users with content by learning from user item interaction histories. However, most systems suffer from the long tail problem, where only a few items, the head items, receive most of the attention, while the majority of the items or tail items remain underrepresented. This results in repetitive recommendation, limiting diversity and personalization. Our objective with this study is to address this problem by increasing the representation of tail items, thereby enhancing the personalization of recommendations. Now, our problem statement and objectives are: the problem lies in inherent bias of most recommendation models toward head item. As these items are more frequently interacted with, this limits the visibility of tail items and can lead to a less satisfying user experience. Our study aims to tackle this by focusing on two main objectives: improving recommendation for tail items and enhancing personalization by capturing user specific preferences. To achieve this, we propose a new method called biased user history synthesis, which prioritizes tail items in user profile, balancing the recommendation output between head and tail item. Now, the literature review of long tail recommendation. In existing literature, the long tail recommendation problem has been addressed with various approaches. Model agnostic method such as meta learning and curriculum learning attempt to transfer knowledge to tail items but can struggle with personalization. Model specific approaches like heterogeneous information network and graph based model leverage complex network to capture user item relationship. However, these existing methods often lack the ability to balance head and tail recommendations effectively or require extensive computation. Our study position itself as an efficient and balanced approach, combining personalization and tail focus through biased user history synthesis. Now, the methodology overview. Our proposed method, biased user history synthesis, builds on a scalable architecture known as the two-tower neural network or TTNN. The TTNN uses separate user and item towers to generate user and item representations, allowing efficient pre-computation. BUHS enhances this by introducing tail item biased sampling and a synthesis model, which augments user representations with interactions that emphasize tail items. This augmented representation captures both general and unique user preferences, allowing the model to provide balanced recommendations. Now, biased sampling strategy. To counter the dominance of head items in user history, BUHS uses tail item biased sampling. This approach increases the likelihood of selecting tail items from a user's history, thus capturing specific user preferences. The sampling process uses a softmax function where items with lower popularity are given a higher probability of being selected. By focusing on tail items, BUHS increases the visibility of these items, enhances personalization, and provides a balanced recommendation list that caters to most common and niche interests. Now, synthesis model options. BUHS offers three synthesis models to integrate the sampled tail items with the user's original representation: mean synthesis, user attention synthesis, and GRU synthesis. Mean synthesis take the element-wise mean of sampled item, offering simplicity and efficiency. User attention synthesis assign weight to items based on relevance, adding depth to personalization. Finally, GRU synthesis treats interaction as a sequence ideal for cases where recent items influence recommendations. Each item has its advantages and the choice depends on dataset characteristic. Now, the training approach. Our training approach uses a max margin ranking loss, ensuring that relevant items rank higher than irrelevant ones. The loss function penalizes cases where irrelevant items rank higher, helping the model prioritize relevant recommendation. To improve diversity, BUHS employs mixed negative sampling, combining in-batch and out-of-batch sample. This approach balances the focus on head and tail item, enhancing more general and specific recommendation. Now let's look at how BUHS maintains efficiency, which is crucial for real-time recommendation system operating at scale. Efficient inference means that the system can generate recommendation quickly even when handling a large number of user and item. The two-tower neural network architecture that BUHS built on is particularly efficient because it allows us to pre-compute user and item representations. In this architecture, user features and item features are independently encoded, meaning we can store representation for quick access. BUHS integrates seamlessly with this setup by also pre-computing the augmented user representation. This means that even though we are enhancing personalization by including tail item, there is a minimum delay in generating recommendation. Essentially, we avoid the need for real-time synthesis and maintain low latency in our recommendations, making BUHS scalable for large applications. Now, the theoretical motivation information theory. Our biased sampling approach is based on mutual information from information theory, which support why we focus on tail item. Mutual information tells us how much knowing one variable like a specific item interaction reduces uncertainty about another variable, such as a user's unique preferences. Proposition 1 in our theoretical framework shows that tail items carry more mutual information about individual users. These items are specific to user's interest as opposed to head item, which are popular and reflect broader trend rather than individual preferences. By emphasizing tail item, BUHS capture deeper insight into each user's unique interest, ultimately providing a more diverse and personalized recommendation experience. This approach combines relevance and diversity, making our recommendation more satisfying and less repetitive. Now the experimental setup, datasets and metrics. To test BUHS, we used two benchmark datasets with varying sparsity and item popularity. First, MovieLens 1M. A moderately sparse dataset contains explicit feedback on movies with user features like age and occupation and item feature like genre. Around 80% of the items are classified as tail item, giving us a good test case for our method. Second, book crossing. An extremely sparse dataset includes both explicit and implicit feedback on books and has a unique user and item set with attributes like user location and book publisher. In book crossing, over 99% of items are tail items, which present an extreme case for testing how well BUHS can enhance tail item recommendation. For metrics, we used hit rate or HR@k to measure the presence of relevant item in the top key recommendation, indicating the system's accuracy. We also used normalized discounted cumulative gain@k or NDCG@k, which account for ranking by rewarding relevant items that are to the top. These metrics were calculated separately for head and tail item, allowing us to measure BUHS effectiveness across both popular and niche items. Now, baseline model. To evaluate BUHS, we compared it with both model-specific and model-agnostic baselines, each addressing the long-tail recommendation problem differently. Model-specific baseline like NUMF or and NGCF are tailored to popular item. New MF combine matrix factorization and deep learning to capture complex relationship but may still focus on head item. NGCF, a graph-based model, incorporate connections between user and items to capture deeper relationship, although it can also be biased toward head item. Model agnostic baseline like DropoutNet and LowQ tackle the tail item problem more directly. DropoutNet uses dropout to simulate missing interaction, improving tail recommendation by reducing over-reliance on head item. LowQ adjust model logits to correct for item frequency bias, but may lower performance for popular items. These baseline comparison allow us to see how BUHS performs in balancing head and tail recommendation compared to existing method. Main result comparison with baseline. Let's move on to the main result. BUHS outperformed all baseline model in terms of both head and tail recommendation. In MovieLens 1M dataset, BUHS showed significant improvement in HR@10 and NDCG@10 score, particularly with the user attention and GRU synthesis model, which best captured user preferences through attention and sequence modeling. This result suggests that attention and sequential context are value for personalization. In the book crossing dataset, BUHS also performed exceptionally well, especially in tail recommendation. The user attention synthesis model excelled here by capturing unique user interest, showing that BUHS can handle sparse dataset and high level of items effectively. These results highlight BUHS ability to outperform baseline like DropoutNet and LowQ in tail recommendation, providing balanced and personalized recommendation that cater to both popular and niche interest. To understand how parameters affect BUHS performance, we conducted an ablation study focusing on two factors, sampling temperature and sample size. Sampling temperature control the focus on tail item. Lower temperature increase the selection probability of tail item, which leads to better personalization in tail recommendation. We observed that decreasing temperature improved HR@10 and NDCG@10 score, as tail item contribute unique user information as shown in our theoretical framework. Sample size referred to the number of items selected from user history for synthesis. Larger sample size provided more general information which benefited head recommendation. For GRU synthesis, larger sample captured temporal pattern, enhancing recommendation. However, the user attention synthesis model worked better with smaller sample size, focusing attention on the most relevant item. Overall, these findings show that by fine-tuning sampling temperature and sample size, BUHS can be optimized for different datasets, adapting to the specific feature characteristic of each user item interaction history. We performed 3 case studies to understand BUHS flexibility, effect on embeddings, and computational efficiency. First, we applied BUHS to different base models, including wide and deep FM, to see if it could generalize beyond TTNN. BUHS improved head, tail, and overall performance across all tested models, with the GRU synthesis model showing the stronger result. This case study confirmed BUHS adaptability to various architectures. Next, we looked at the impact of BUHS on final item embedding using UMAP to visualize how head and tail items are distributed. With BUHS, tail items showed clearer clustering and separation from head item, particularly with user attention and GRU synthesis model. This structured distribution allows the model to represent diverse preferences effectively. Finally, we examined training efficiency comparing BUHS computational cost to baseline model, especially the mean synthesis variant. The user attention and GRU variant have slightly better training time but still outperform many baseline inefficiency. To better understand how BUHS influences item embeddings, we used UMAP projection to visualize the distribution of head and tail item. With BUHS, we observed that tail item represented by blue dot were more distinctly separated from head item, which are shown as red dots. This separation was particularly strong with user attention and GRU synthesis model, which means that BUHS creates a structured representation space where the model can effectively capture unique user interest. Tail items also space where the model can effectively capture unique user interest. Tail items also showed greater variance in their embedding, indicating that they are not overshadowed by popular item, allowing the model to make diverse and personalized recommendation. Without BUHS, embeddings for head and tail item were more mixed, showing less distinction between popular and niche item. This structured embedding space makes BUHS more effective at balancing head and tail recommendation, ultimately leading to a more satisfying user experience. Training time is another important consideration, especially for recommendation systems that need to handle large volume of data quickly. We compare BUHS training time to that of various baseline model. Many baseline models such as MGL and Dropout Net had higher computational cost, taking significantly longer per epoch due to their complexity. In contrast, BUHS, especially with the mean synthesis variant, adds minimal computational overhead. The variant's training time was nearly the same as TTNN model, which demonstrate BUHS efficiency. Now concluding, in conclusion, BUHS offer a balanced solution to the long tail recommendation problem, enhancing personalization by focusing on tail item. Our method improves tail recommendation, increases personalization, and is flexible enough to integrate with various recommendation models while maintaining computational efficiency. BUHS creates a structured embedding space that helps balance head and tail item, leading to diverse and relevant recommendation. Looking forward, we see several opportunities for future work. One area is integrating meta-learning techniques to make BUHS even more adaptable, particularly for cold start users who have limited interaction history. Another direction is exploring more synthesis model, such as advanced attention mechanism, which could further enhance personalization by capturing complex user item pattern. Finally, we aim to adapt BUHS for domain specific like e-commerce or video streaming, where unique user behavior may require specialized tuning. Overall, BUHS provide robust, scalable and adaptable framework that can significantly improve the user experience in recommendation system. Thank you for your attention.